Since machine learning can be applied to a lot of problems, there are a lot of machine learning algorithms available. A quick check of one of the standard libraries show that there are over 50, and more being created. So how do we decide which algorithm to use? To decide which algorithms would be suitable, we can compare the algorithms on a number of factors. Not surprisingly, data scientists have different opinions on which factors are important in selecting algorithms. The decision factors presented here represent one possible set of factors. As you gain experience, you will likely develop your own set of factors and decision criteria. For our example, we're going to use these decision factors. We will evaluate algorithms based on what type of learning they support, result type the algorithm produces, the complexity of the algorithm, and whether the algorithm is basic or enhanced. We will use our solution statement and knowledge of the workflow to help guide us in evaluating these factors. Each algorithm has a set of problems it works best in. One way to divide them is to look at the type of learning they support. With that in mind, let's go back to the solution statement and see what guidance it offers. Reading the statement, we see our solution is about prediction. Prediction means supervised machine learning, so we can eliminate all algorithms that do not support supervised machine learning. That reduces the number of choices, but we still have a lot. Let's see what else we can do. Let's see how the result type can help. Prediction results can be divided into two categories, regression and classification. Regression means a continuous set of values. Back in our example of determining the price of a house, we use the features of the house, size, number of bedrooms, etc. We put those features into an equation and produced a price. Any change in any feature resulted in a direct change in the price. In contrast, classification problems have a discrete set of values such as small, medium, or large, 1 to 100, 101 to 200, 201 to 300, and more importantly for us, true or false. Changes in a feature value may or may not change the classification. So what type of problem do we have? Again, the solution statement comes to our aid. From the solution statement, we see that the algorithm must predict whether a flight would arrive 15 or more minutes after the scheduled arrival time. Remember that we're using arrival delay 15 to define if a flight is delayed. An arrival delay 15 is a binary outcome. Since we are predicting a binary outcome, delayed or not, we can eliminate any algorithms that do not support classification in general and binary classification in particular. That knocked out some more, but perhaps not as many as we might have thought. That's because many algorithms support both regression and classification. We're down to 20 algorithms, but that's still too many. Since this is our initial algorithm, let's keep it simple. Let's also eliminate ensemble algorithms. These are special container algorithms that contain multiple algorithms under a single interface. These algorithms are most often used when we need to tune the model to increase performance, and we are still trying to do our initial training. Also, ensemble algorithms tend to be complex and difficult to diagnose and troubleshoot when the results start going awry. We still have a few algorithms left. We can divide these into two groups, enhanced and basic. Enhanced algorithms are variation on the basic algorithms, and they have been enhanced to perform better and/or add additional functionality. As a result, they are more complex to understand and use properly. Since this is our initial algorithm, let's stick to basic algorithms. These have the advantage of being less complex and therefore easier to understand. For our problem, let's look at these three basic algorithms as possibilities for use in our initial training and evaluation. We'll look at naive Bayes, logistic regression, and decision trees. Each of these algorithms are classic machine learning algorithms, and understanding a little bit about each one can greatly help understanding more complex algorithms that use these algorithms as building blocks. The naive Bayes algorithm is based on Bayes' theorem. This theorem calculates the probability of the flight being delayed by using the likelihood of delay based on previous data combined with the probability of delay based on nearby feature values. It makes a naive assumption that all of the features we pass in are independent of each other and equally impact the results. This assumption that every feature is independent of each other allows for fast convergence and therefore requires a smaller amount of data to train. The logistic regression algorithm has a somewhat confusing name. In statistics, regression often implies continuous values, but logistic regression returns a binary result. The algorithm measures the relationship of each feature and weights them based on their impact on the result. The resultant value is mapped against the curve with two values, 1 and 0, which in our case is equivalent to delayed and not delayed. The decision tree algorithm can be nicely visualized. The algorithm uses a binary tree structure with each node making a decision based on the value of the feature. At each node, the feature value causes us to go down one path or another. A lot of data may be required to find the value which defines taking one branch or another. As we see, the decision tree has the advantage of having tools available to produce a picture of the tree. This makes it easy for us to follow along and visualize how the trained model works. From these three, let's select the logistic regression as the initial algorithm for training and evaluation. Logistic regression has a number of characteristics that make it useful as an initial algorithm. First, it is simple to understand. Once the value hits a certain threshold, the result is true, delayed in our case. Below that threshold, the value is false, not delayed. Second, the algorithm is fast. Training time of some of the more complex algorithms can be 100 times or more longer. And in machine learning, you often have repeated cycles of running the algorithm, evaluating the results, and tweaking the parameters. Having a fast algorithm makes these cycles much quicker. Finally, the algorithm is stable. With some algorithms, as you work with the data, small changes in training parameters can cause the results to vary wildly. Or worse, the algorithm fails and returns nonsensical results. Both of these can send you on a long and frustrating debugging cycle. Logistic regression does not exhibit these behaviors. Let's summarize our algorithm selection process. First, we need to acknowledge that there are a lot of algorithms available and more being created every day. With all these algorithms available, we need to select the one that will be initially trained with our data into a model. To select this algorithm, we can use the features of our problem that we captured when we defined our solution statement. From the solution statement, we know we have a supervised machine learning problem, which removes all of the unsupervised machine learning algorithms. We also want binary result, not continuous results, which further reduces the number of viable algorithms. Since this is our first pass at algorithm training and evaluation, we also eliminated all ensemble algorithms, which combine multiple algorithms. We also decided that for initial training, we only wanted basic versions of the algorithms. After evaluating the algorithms, we selected logistics regression as our initial algorithm because it is simple, fast, and stable. In the next section, we will train the logistics regression algorithm with our data and see how well it can predict if a flight is going to be delayed.